I'm Roman Maeder from Wolfram Research, and today I will present on counting truncatable primes. That's something that started as a discussion on the Wolfram community and which then ended up as several months worth of computing, and there's still more work to be done. So this is a progress report on how far we have got. So this grew out of a community post, Wolfram community, and there were two people, Sandro and Marco, who contributed to that discussion, and it went on for quite a while. And then I started to actually do a little bit of more computations in this particular field. So what is the reason for doing this? So the reason is that there was some number file video where they displayed this particular pencil. You can actually buy those, and this is a prime number that you see here. And when you sharpen the pencil, eventually the bit will chop off that first digit, right? When the pencil gets shorter and shorter. And what you then see, what remains is another prime number, and so on until the very end to that 7 down here, which is also prime number. So all of these truncations from the left are primes. And this happens to be the longest truncatable prime in base 10. So here is that computation which verifies that claim. So I start with that number, I truncate it from the left, and then eventually let me just redo that, and I'll just apply prime Q to all of these, and it should all be true. So question now, how many such primes are there, and how long are the longest ones, and what about other bases than 10? And for smaller bases where there aren't that many primes, you can actually store all of those. Now, it doesn't really make a lot of sense to store all of those because most of these are truncations of other ones, right? I mean, they are called truncatable primes for a reason. So there are some maximal ones which cannot be extended, so you can think of it as a form of a tree, and eventually there will be the leaves of the tree. These are the maximals, and if you cut off branches from the bottom, then you get all the other truncatable primes. So I was also interested in not only all the truncatable primes, but also all the maximal ones. And how do you search for these? Well, you start from the ground up. You start with the 0 or 1 digit primes, and then you have all the digits from 1 to base -1, so there are b -1 digits. And to go from k to k plus 1, you just look at all the candidates. You have one of the k-digit primes. First digit is 1, then digit 2, up to b -1. And there are b -1 such numbers, and then you just test them for primality. That is quite fast. And I mean, I once wrote the original version of that prime test probably 20 or 25 years ago. It has since been improved, and so this is quite fast. And if none of these extensions are prime, then P itself is a maximal truncatable prime. Otherwise, it's not maximal, and we continue the search with all the prime candidates. And there are two natural ways of doing the search. Breadth first, so going from k equals 1, k equals 2, k equals 3, and so on. And depth first, recursive search, so you always go down the leftmost branch of the tree. And these are useful for different situations. If you want to generate all of them or parallelize the search, then breadth first search is the way to go. If you just want to find out how many there are, then you can do a depth first search. The advantage of the depth first search, it doesn't require any intermediate memory other than the stack. And we will see that there are quite a large number of these primes. So here's an outline of a very simple procedure for doing a recursive search. So I start a recursive search, all primes for a given base. I have some global variables for the kind of results. I'm interested in the length distribution, so how many primes of length 1, 2, 3, 4, and so on. and what are the longest ones. So these are the kind of global high watermark variables. And here is my recursive search procedure, and all the magic happens inside these statements. So digits is a list of all the digits, multiply it by beta and add p. That gives me the b-1 candidates. I test them for primality. And if there are no new primes, then this one is maximal, and so I update the global variables. And if there are any, then here is the recursive call of that procedure to all the new candidates. And I start with the initial prime 0. I do not count it because it's not real prime, but it can be used to start a search. And I return the results. Now, I don't want to spend time explaining my code, but I should. Let's see. Let's redo it here. And so what you get as the result is the number of leaf primes for base 10, total number of truncatable primes, the longest length, the list of primes of that length. There happens to be just one. And here is the length distribution of the leaf primes, and here is the length distribution of all primes. So you can see there are obviously 4 one-digit primes, and 2 of those are leaf primes, because with 2 and 5, these are not co-prime with a base, so they die out. There are no other primes that end in 2 or 5, except 2 and 5. The other 2 one-digit primes give rise to 11 two-digit primes. All of those can be extended. There are 39 three-digit primes. One of those is maximal. The other ones go on, and so on. So this is the kind of result that I'm interested. Here is base 16. There are quite a bit more primes in base 16. Oh, I somehow didn't evaluate the initialization cells. Now I have no menu here in my. Well, okay. Okay, here it is. I did pre-compute it, so it should still work here. So this is the longest prime in base 16. It's just a little bit longer, but there are quite a bit more primes here. In base 19, there are very few, just 685, but there are 4 longest ones, and you can see that that's very typical, that 2 of those have the same branch, right? And just the initial digit, which is different here. And another one is also part of that branch, and then there is a 4th one that happened along the way. But the striking thing, which if you look at that discussion in the Wolfram community, you can see why is there such a big difference in the number of primes for different bases. And so I started to think about really attacking larger bases where there are a lot more primes. And so I obviously have to do it in parallel. So I found the best method to do is to just start a breadth first search, say for the first 4 for lengths 1, 2, 3, 4. That gives me a number of candidates. And then I do a depth first search for each of those, and they are completely independent. And the jobs do checkpointing and so all that, which is necessary because some of these jobs run for months or even years. So you need all of these techniques for organizing large jobs. And what I wanted to do is exactly what I showed before. I want to know the number of truncatable primes broken down by length, the maximal lengths, and all the longest ones. And I always work with integers and not digit strings. It's never necessary to actually convert to base B, only when I want to see the result in a nice form. So we then found that these numbers of truncatable primes for various bases has already an entry in the online encyclopedia of integer sequences. Okay, so that's a mouthful to say. And so we looked at that, and there was the one case that was missing was base 24. And so we wanted to know how long does it take to compute that. And with 4 digits, there are just 3,808 primes, so that's a good number to start these parallel jobs, because I want the parallel jobs need to have a certain runtime. They shouldn't be trivial, otherwise there's too much communication with the master kernel. But I don't want the individual jobs to run for days because I'm interested in intermediate results and see how it progresses. So here it was just 2 minutes on average. This is the runtime distribution. And the total sequential runtime was just 127 hours, which means that on a machine with 22 processors, it's an overnight job, just 6 hours of computing time. So what are the results in base 24? There is just over 1 billion truncatable primes. The maximum length is 53. There are 2 maximum primes of length 53. Here they are in base 24. And so that, and if you wanted to store them, it would actually be feasible. It's just 8 gigabytes of memory needed to store them as base B strings if you wanted to do that. So that was encouraging to see that this computation, which apparently has never been done before because that entry was missing in that encyclopedia, that was entirely feasible. And so we wanted to look at some of the more challenging bases. So now so actually here is an interesting graphic coming out of this result, because I have, for each length, I have the number of leaf primes and non-leaf primes. So if you look at one particular length here, then you see the height here is the total number of primes of that length. And the yellow ones are the extensible ones, which are the seed for the next k+1. And the blue ones are those that die out, that are maximal. And as we will see, the probabilities of these numbers being prime will slowly decrease. And so after this growth, it will slowly die out. And eventually at 53, there is just one left that is maximal. And so the computation stops. Now, the big question was, why are there so big differences in the number of primes for different bases? And this is actually quite elementary number theory. These candidates that we search, a plus b, a plus 2b, up to a plus b minus 1, form an arithmetic progression, and there is a theorem about the number of primes in an arithmetic progression, which is true whenever the increment and the starting value are coprime, which is true in our case for large enough k. And so this theorem applies. And there was there's some prior work about truncatable primes, which I found in 1977 that was already considered at that point. So this formula should give me an idea of how many primes to expect. And here it is now for bases from 1 to 100. So I just chose one arbitrary k 20, and here is are the values for this formula, and you can see the value 24, which is here, which was obviously the most difficult one of those before it, but then there's this length 30, which seems to be quite hard, and then 42, and so on for 54, 60, and 90. So why is it, where does this distribution come from? And before I answer that question, I wanted to show you that this actually agrees very well with the results. So here is the same blue points, but I also have yellow points. These are the actual results from the computations. So you can see here 24 is that result here. The largest one I've done is 85 up here. The next one that could be doable is 40, and 30, as we will see, requires a little bit more computing infrastructure. So the correspondence between the theoretical results and the measurements is quite good. So here is the reason that this happens for different bases. Now, one of the terms in that equation was the Euler totient function of b to the k. And there are many ways to write that function, but the most convenient for this particular application is in this form. It's b to the k times the product of 1 minus 1 over pi, where pi runs over all distinct prime factors of b. And so if a number has many distinct small prime factors, it will have more primes. And so even bases have more primes than odd ones, because the smallest prime possible is 2. So 1 minus 1 over 2, that cuts off quite a bit more than any other prime. And the next one to consider is 2 times 3, or 2 times 3 times 5. That is 30, and that is the reason why that case 30 is so difficult. And the next difficult one would be 42, which is 2 times 3 times 7. And indeed, 30 is the smallest base for which we do not yet know how many of these truncatable primes there are. So here then is a big table of the results that we have done so far. You can see that there is 29 and 31, so 30 is missing, but everything before is there. There are many cases where I didn't even have to parallelize. So you see here there is just one job. I don't know how to make this table bigger. I don't know whether you can read it. But here some cases I did parallelize. This is the total runtime, which is not very exact because I use different machines, so it's not necessarily comparable. Then here is the number of primes, leaf primes, total primes, the maximum length, and the list of those primes of maximal length. So you see base 18 has quite a large number of primes, and 24, of course, is the record holder so far. Then if we go on, then we see there is the biggest one I've done, which took me more than a month on that 22-core machine, 93 billion primes. There are some bigger ones here, 37 billion for base 44 and 30 billion for base 46. And the longest is 65 here for base 46. There's a prime with 65 digits in base 46. So what we now will do eventually is to try to update those entries in the online encyclopedia of integer sequences, because they contains quite a fewer results than I have here. Now there's a disclaimer I have to make. Prime Q is a probabilistic prime test, so these numbers are strictly speaking upper bounds. But I did take all the longest ones that you can see here and subject it to a deterministic primality test, and also its truncations. So all the numbers that are here are guaranteed to be prime. So here is my wish list. I then took from the theory the expected complexity. This is an exponential measure, so even though these numbers are closely together, there are you can see here the value 30 is, you will see in a minute how long it will take, and then there is the value 60 down here, which is the next more difficult one, which we will see is completely impossible within the lifetime of the universe. So this is quite a big increase in the complexity. Now there are cases that will eventually also be doable, like 42 here. 40 is here. That's actually the next one to attack after 30, and so on. So this is the kind of wish list, but what does it take to actually solve or make progress on this wish list? Here is my estimate for how long it will take for base 30. So I just started with a random sample of these primes and let it run for about a month or so, just to get a feel of what is involved, and then I did an extrapolation. So I would expect there to be about 23 trillion of these primes, and the computation should take about 750 single core years. So if I want to have a 1 month project, I would need 10,000 CPU cores, and if there's anyone in here who is sitting on unused machine with 10,000 cores, then please let me know. I mean, there are some companies, there are some businesses on this planet that are big enough that we will tap for and ask for help. There's some obvious choices here. And then the next ones to attack are these. I mean, eventually it will stop being useful because it will just, the computation time will just grow to very large values. I mean, if you're talking about millions of years or so, and that's no longer worthwhile. So there are better things to do with your idle CPU cores, but 30 would be nice to tackle. And space 60 is hopeless. I haven't even been able to derive an estimate because everyone, however deep I went with the initial search, each one of those recursive searches never finished. All I know is that the length is at least 92, and that should give you an idea if you compare it with the kind of 50 or 60 that we have with the other cases, that this will just take longer than the lifetime of the universe, probably. And I feel obliged to end with a picture of pumpkins because of Halloween celebrations today, and also because this is quite a bit spooky that you see these large values that we know are outside of our reach. And that's the end of my presentation. Thank you.
Got a few minutes for questions.
Okay, questions.
Are you using standard CPUs? Do you have a cluster or something to work?
I mean, I'm using the prime Q function of Mathematica for all of these, for all the primality tests. Okay. So it's a standard parallel Mathematica computation. I have a master kernel that distributes those primes, and then there are all the slave kernels that do the jobs, and when they are done, it's written to disk as a checkpointing measure, and then it does the next one. And that just runs on my machine at a low priority. So.
Have you tried to use a GPU to accelerate the process?
No, I haven't. I mean, I personally, I've never used GPUs for anything like that, and I'm not aware of, are there any primality test packages for GPUs?
Okay.
I don't know. I don't know how much that will give. It's not that kind of, GPUs are good when you have the same thing to do for multiple data, but here each prime test runs completely differently, right? It has the Miller-Rabin test and all of these things. Maybe there is something like that, but I don't know. I mean, yes?
How reliable, say, if you did a prime Q on 10 to the 100th power, how reliable is that estimate?
Well, I think there are no known counterexamples to that primality test that we use. I actually don't know exactly what the current test is, but this is a standard procedure. There are two tests, Miller-Rabin and another one, and if you combine those, then we know pretty much that, I mean, there are no known cases where it doesn't work. So it's, and here especially if we do it, with these truncations, then the chances that such a sequence would all be wrong is quite low.
Well, it seems to stop at a pretty reasonable number, even though it's large,
Mm-hmm.
to work with. But you're not dealing with any instances apparently that run into.
No, I mean the longest one we've encountered is 65 digits to base 40, which translates to how many digits to base 10? Probably. I mean, not that much. No, I mean, yes. I mean, the deterministic test at the end was quite a challenge. I mean, there's a package in Mathematica for the provable prime Q, which gives you a certificate. It's a clever bit of class field theory to derive at the computation that proves that a certain number is prime. Now that code is over 20 years old, and there are flows of control in that code which have apparently never been exercised because they didn't work. So I first had to debug that package before I could use it for this particular. Now the package will be replaced by something. There will be some new number theory functions in future versions of Mathematica. But once I solved that problem, it was actually quite feasible within a few minutes for each of those maximal primes to test them exactly for primality without any doubt.